All right. Hello, everyone. Welcome back to the Galaxy Science Interest Group bi-weekly seminar. Because of some interesting scheduling issues in the beginning of the semester, we actually, the opposite of front-loading our schedule. So you're getting this bi-weekly seminar toward the end of the semester and into the summer now. So, we are looking for speaker for next semester and next year. So if you're interested in giving a SIG seminar, or you know someone who gives a really good talk, please send in your nomination or self-nomination to Benny or myself, and we'll dump into a list and figure out the schedule for next year. Great. So without further ado, let me just introduce Kartheik. So Kartheik and I have known each other since grad school. Actually, we were office mates back in Rutgers. Kartheik is 1 year more senior than myself. And after Rutgers, Kartheik took up a fellowship in, is it Dunlap? No.
Yeah,
Yes,
Toronto.
okay. Right. In Toronto, and then later got a Hubble Fellowship and took it to Columbia University. And are you still taking on the CCA Fellowship?
It's in the works. So
In the works. Okay. So Karthik might soon move to the Flatiron Institute and might already have other future plans. But well, besides that, Karthik worked on so many different science fronts, most notably known for Dan spaces, the non-parametric SED fitting code, but also many other things. So I'm not going to summarize that. I'm not going to do that from memory. I will let Karthik tell you about his most exciting work that he wants to share with you. All right, take it away, Karthik.
amazing. Let me get my screen sharing started. All right, good. Can folks see my screen?
Yep.
Excellent. All right, I'm also going to put the chat up so that if people have any questions, I want this to be pretty interactive. So at any point, if you have questions, either unmute yourself or put it in the chat or something. Uh, yeah, let's have fun with this. So my name is Kartheik Iyer. Thank you for the wonderful introduction. I am very happy to be here and sort of talk about future science because I think that's one of the most fun parts of doing these big community things. So I want to talk about some of the things that we're doing in terms of what we think of as the cutting edge in galaxy evolution science, and then sort of see how far we can push that forward. So let's jump straight in. I also want to say that, astronomy is a very large collaborative science, and so none of the stuff that I'm talking about would be possible if not for the support and advice of the whole, the host of people, especially students and people who develop and maintain software that we all use as a community. So it's really nice to sort of be part of this. All right. So habitable worlds in whatever form it shapes out to be is going to have a focus on studying galaxies as cosmic ecosystems, right? So the nice part of this is that there is very much a focus on sort of understanding how galaxies form and how they evolve, how they interact with their environment, and how they form stars within them, and how all of this is regulated and how the different scales involved all interact with each other. So this is, really nice for me in the sense that it acknowledges the many subtleties that are still left to understand in galaxy evolution, and it's taking a lot of community input, and so that's a very useful place for all of us to come together and talk about some of these things. The reason we care about all of this is because galaxies are very complex ecosystems, right? So they tend to have many moving parts, and all of these moving parts are sort of linked across multiple scales. So you have inflows of gas that come in on really large scales. You have the collapse of gas and star formation in the ISM of the galaxy. That sometimes leads to feedback in the form of galactic winds that blow material out. Some of that falls back in through a process that we call baryon cycling, and some of it gets driven out of the galaxy through outflows. And in all of this, there's also central supermassive black holes that certain galaxies intend to sort of affect how it's able to form stars and have a quite interdependent relationship with the rest of the larger galaxy. So the a really cool result of this is that even though we know all the physical processes that sort of make and shape these galaxies, the interplay of these different processes means that you can start with the same set of ingredients, and depending on their relative fractions, you can end up with galaxies that look quite different from each other. So we see this incredible diversity of galaxy, both visually when we look at galaxies, but also in terms of morphologies, physical properties, star formation histories, whatever we talk about, right? And so it's been a key driver of our field to sort of try to understand what are the physical mechanisms that um give rise to this diversity, and how is that related to the way they formed over time. So how is that related to their past? And like I mentioned, there's sort of many different physical processes that we've identified. A lot of these we have managed to sort of come up with implementations for in our big cosmological simulations. And so we're able to sort of put these in and see, how it affects a population. But we also don't know precisely what ranges they act over for specific populations of galaxies. And a lot of times we don't really know how they interact with each other. So this is one of the things that I've been trying to study. And so we take that broader question and we break it down into two slightly more tractable ones, which is how do we infer the past lives of galaxies from multi-wavelength observations? And then how do we tie that to the underlying physical processes that are regulating star formation? So the key sort of driver of all the observational stuff I've been doing is the fact that galaxies tend to look very different at different wavelengths. And this is because the emission that we see from galaxies at different wavelengths tends to be from different physical components. So if you can observe the same galaxy, across a broad baseline, and even sort of at high resolution in a narrow baseline, sometimes you're able to disentangle the emission that comes from things like the hot gas surrounding stars, from the stars themselves, from dust, from active galactic nuclear components. And so this allows us to sort of probe the many different observable parts of a galaxy, back out some information about how it formed, and then tie that to the underlying physics, right? Specifically, I've always been interested in galaxy star formation histories. And this is essentially looking at the UV to near IR stellar continuum and saying that, okay, so because stars of different ages tend to peak at different parts of the SED, the spectral energy distribution, you can use Bayesian techniques or matrix inversion or whatever you're comfortable with to sort of disentangle the relative contribution of light coming from young stars, from intermediate age stars, and from old stars, and then use that to back out some measure of a galaxy's star formation history. So this is how you infer information about the past. And so what we end up doing is essentially taking these multi-wavelength observations, backing out some information about a galaxy's physical state and its past and its properties, and then looking at physical implementations of galaxy evolution in these big cosmological simulations, and trying to sort of match the distributions of physical properties that we back out to try to understand something about the physics. So the way we generally do this is we perform something called SED fitting, or spectral energy distribution fitting, to go from these multi-wavelength observables to physical properties, so things like stellar mass, star formation rate, star formation history, and so on. And then we do this for a whole population of galaxies, and we build up things like scaling relations, such as the correlation between stellar mass and metallicity, or stellar mass and star formation rate, and or things like mass or star formation rate functions. So this is sort of been the standard pipeline that we do. What I want to encourage you all to think about is how we can broaden this. So one way of doing this that I want to talk about is going from images to physical properties instead of just the SEDs. And this is something that John Wu talked a bit about in his Galaxies SIG a few weeks ago. And I sort of want to build up on that a bit. The other thing you can do is inference at the level of entire populations. So instead of trying to do, fit individual galaxies and get their properties and then aggregate them, you try to make a model for the whole population, and then you try to back out quantities that you think are uniform at the level of that population. And finally, I want us to also think a bit more about how do you actually go from these scaling relations or mass functions and or the physical properties of individual galaxies to constraints on things like feedback and cosmology, things that we really want to learn, right? So you can always do a one-to-one comparison and see whether something matches or not, but then that's not really a constraint. So you want to go beyond that, especially as we think about these bigger, more powerful surveys. So there's a bunch of work that I've done that I think I'll briefly cover. But more importantly, I feel like with facilities like HWO, you can start thinking of what you would need to do these kinds of analysis, what would make them better. So whether that's high angular resolution imaging or even methodological improvements or wider fields of view, this is sort of the stage where we can brainstorm about these things. And finally, I do want to say that, what I'm talking about is hardly unique. There's a whole bunch of SIG talks that sort of cover different parts of this. So I've briefly put, the ones that I could find easily. But if you look at the list, the full list on the website, there's a bunch of relevant talks that you can go and look at if you're interested in any one part of this, and they've all been helpfully recorded by Bene and Aaron, so it's all there for posterity. All right, so let's jump straight in. Um, so as I mentioned, galaxy spectrum, contains a lot of information about how it formed, and stars of different ages tend to peak at or contribute at different parts of the spectrum. So you can try to back out the sort of individual contributions, and from there get to the star formation history. Now, the issue is that the way I showed here, right? Like here, I'm showing three populations of stars, and that means that if you can back out a very limited amount of information about the history, the way you represent that information makes a big difference. So, given that you have a very limited amount of information available in galaxy spectra or in photometry, you want to come up with a representation or a basis that is maximally informative and allows you to do inference in a principled manner. So, uh, my sort of pitch for this is something called the dense basis method, where you describe a galaxy's history in terms of quantiles when it formed, uh, certain fractions of its stellar mass. So T25 is when it formed a quarter of its mass, T50 is when it formed half of its mass, T75 is when it formed 75% of its mass, and so on. And this essentially gives you a set of integral constraints. So you're going from 0 to 1 in fraction of mass formed, and you have a bunch of time points when it formed different fractions, and then you can essentially draw a line through all of them to connect it, take the derivative of that, and get the star formation history. So this allows you to sort of describe any shape in SFH space without assuming any particular functional form for doing so. And so the nice thing is, I'm basically showing how the spectrum of the SED changes as you change, different quantities in this parametric description of the star formation history. So here, if you change the specific star formation rate, you can sort of see how the UV flux shoots up as you increase SSFR. And then slightly more complicated, this is where if you're changing T50, so the time when it formed 50% of its mass, you can sort of see how it changes the overall rest optical part of the continuum, and that it also does so in a pretty nonlinear way. So essentially, when T50 is really old or really young, you can essentially see its signatures because it either looks like a very old quiescent galaxy or like a booming emission line galaxy, but then in the middle, it's actually much harder to constrain. So this is something people generally don't appreciate, and it can, if you don't account for these things properly while designing priors for your fitting, then you can actually end up with pretty significant biases in the recovered distributions that you get. So the upshot is this kind of parametrization allows you to get a whole bunch of different staff formation history shapes with as little as 3 parameters. So in this case, I'm actually just varying 2 parameters: uh, the staff formation rate, which I go from actively staff forming to quiescent in this row, and the T50, which is when it forms 50% of its mass. And you can get all of these different shapes just with these 2 parameters. And then you can scale the whole thing by adding a third parameter that represents stellar mass. And so these sort of allow you to create a whole bunch of flexible stuff machine history shapes. And all of this is available in a public code that is meant to fit large catalogs of galaxies just by virtue of the fact that it pre-computes a set of SEDs and the associated parameters so that when you're doing inference, it's actually much faster. And it allows you to explicitly set the priors and covariances if you know that you're working in a particular regime where you can use informative priors. So this was something that I developed over essentially the time leading up to the pandemic, and then applied to a whole bunch of different problems. So the first thing is quantities that depend on the staff formation history are much better constrained when you have these non-parametric methods of describing the shape of the history without you invoking a particular functional form. So this leads to better constraints on things like stellar masses and staff formation rates that can otherwise be biased because of parametric assumptions. It has also been used across a whole bunch of high redshift galaxies to sort of characterize their properties, sometimes inferring things like redshift or the star formation history itself, or in one really interesting case, looking at a doubly lensed galaxy and comparing the star formation histories across the multiple images, which was very cool. Or even doing star formation histories in a resolved sense to get the distribution of stellar mass across an image. On a population level, this can be used to create maps of essentially how galaxy histories change as a function of redshift and as a function of stellar mass on almost a population level. This is showing how galaxies in the candle survey sort of go from being extremely star forming at very high redshifts and low masses to firmly quiescent at low redshifts and high masses, and you can sort of see the transition as that happens. And you can use this to sort of break down the fraction of time that galaxies spend in different parts of parameter space. So basically, how much time they spend as starbursts versus as regular star forming galaxies, or as they are quenching. And this allows us to sort of compare with theoretical models for the physical processes that uh, cause starbursts and quenching, and see if the statistical distributions make sense. The final cool thing is that for a long time we treated galaxies as single points at the epoch of observation. So if you see a galaxy at a certain redshift, you can estimate its stellar mass and star formation rate, and it becomes a point on a scaling relation. And then we make observations across many redshifts and try to connect them as population averages. But if you have the star formation history, you can sort of trace the evolution of a single galaxy over time and see how it ends up, and how they sort of how the average galaxy does some really wild and wonderful things compared to the population average. And finally, when I wrote the CAMELS paper, I briefly used Jehan Kartaltepe's visual classification catalog to see whether there was any correlation between how a galaxy looked and how it formed, and started seeing this correlation, between morphology and histories that I thought was pretty interesting. And so I've always wanted to investigate that further. And so that brings me to the second part of this, which is the image-based inference. So everything that I described so far was very much at SAD level, but in principle, you could try doing the same thing with images. So this was work with a fantastic student, Juan Alfonso, who's now doing his PhD at Tohoku University in Japan. And what we did was we trained a neural network to take images of galaxies, run them through a convolutional neural network. So there's an amazing introduction to this in John Woo's talk. So I'm going to encourage you to go listen to that for the nuts and bolts of this. But then, so we pushed it through a CNN and we asked it to predict the star formation history. But we didn't stop there. We said, okay, so we have the history, but now can we go back and look at the part of the image that actually led to that prediction, right? So here's an example of this sort of saliency approach that we use to make our process interpretable. So we have a single clumpy galaxy in the GRI bands, and red means more flux in that pixel would lead to a higher estimate of the quantity that it's predicting. So in this case, SFR, and in this case, D4000. So one observed, one derived. And blue means that, higher flux there will lead to a lower estimate of the quantity. So this is basically saying that more flux in the clumps would mean higher SFR, and more flux in the bulge would mean lower SFR, which is sort of what you'd expect. And so it's learning, real physical trends that these mappings between the morphology and these SED derived parameters tend to have. And so the nice thing is you can now go to a parameter space, something like the stellar mass versus star formation rate plane, and you can start coloring all the galaxies there by their saliency maps to see which parts light up. And you can use that to study trends in how the morphological information about a particular quantity evolves as you go along this parameter space. So this was really fun to do. But these are all point estimates. And so what we have been doing now is trying to extend this to a full Bayesian approach where you can give it an image and it spits out essentially a set of posteriors for both morphological and SED based parameters. So you have both SIG and stellar mass and T50 on the same plot, which is something that hasn't been done so far. And so in this case, you can see that this one's a old metal-rich elliptical galaxy, and so you see that sort of manifesting in the SIG, metallicity, and T50 posteriors. And then if you give it something like a nice face on spiral, then you can see that, oh, okay, it's shifted from being an old galaxy to a young galaxy in the posteriors. It's much more metal poor compared to the elliptical, and the SIG is peaking around a value of 1. You can also give it something more confusing. So something that is still a spiral, but no longer blue and star forming from its SED. And so here it gets a long tail of for the T50 saying like, oh, I'm kind of confused about what's going on, right? So it's still saying that it's young, but it's also getting a long, which comes from the morphology, but it's also getting this long tail, which comes from the color. You can also give it things like edge-on galaxies that are quite dusty, and it tends to pick up on that. And merging systems where the training set we used essentially was IFU data. So it's essentially learning to predict the entire mass in this field of view. So it gets the combined mass and properties of a lot of the light from both of these galaxies. And then when you give it really low signal to noise things, it does, the posteriors are much wider. It's much more uncertain about, in this case, things like the T50 and metallicity. It has a reasonable handle on things like the stellar mass and SFR. And then if you give it something even fainter, then it's like, yeah, I really don't know what's in this image, and I'm going to just predict really wide uncertainties for everything. So this is sort of well calibrated in the sense that it's not artificially confident about things that it doesn't get information about. And you can sort of use this behavior to do all sorts of validation tests, where if you pass in essentially uncorrelated noise, you should get the conjugate of your prior as the posterior, and that's sort of what you see from these tests. So the nice thing about this is it allows us to build up maps of how much information or how much certainty there is by looking at the width of the posterior at different parts of parameter space. So this is saying that, okay, if I care about, say, T50, for example, then the width of the posterior is reasonably small if I'm above average star formation or if I'm fully quenched. So there's some morphological information that lets me constrain that. But then if I'm in the Green Valley, then it's really uncertain because there's a bunch of different E50s for galaxies that can be there, and the morphological information it tends to be quite disturbed. So there's a lot of physical, insights to what we're seeing in these posterior plots. And I guess one just cool plot that I saw when I was doing this was that when you're trying to constrain the amount of dust, the uncertainty tends to increase along with the actual values as the galaxy gets more edge on. But then it's also lower for galaxies where most of the light is in the bulge. So this is like a neat data-driven validation on a population level. So that's sort of the image-based inference. There's a whole bunch to be done here. If you're interested in any of those, please talk to me. I'm quickly jumping to population level inference. So now moving away from single galaxies and looking at uh, uh, ensembles of galaxies. So what can you constrain from an ensemble? Well, something that tends to hold for some kind of physical mechanism that tends to hold for a whole population. So one example is that we know that star formation histories are bursty, by which I mean that they tend to show variability over a wide range of timescales. And we think that a lot of these timescales come from physical processes. So Sandhu Takela and collaborators wrote a paper talking about how you have variability on different timescales by processes like the creation and destruction of giant molecular clouds or the cycling of gas between the ISM and CGM, or even just the physics of of gas inflow on a halo scale. And then when we studied simulations, that also tends to back up this behavior. So what we started doing is saying, okay, you can use smart numerical methods to try to model this burstiness. So you can model both the amount of variability as well as the timescales on which this variability is correlated. And you can try to constrain that using a population of galaxies. So we came up with this package called GP-SFH that it essentially has a 5 parameter model that accounts for two sources of variability. So one on a galaxy wide model scale and one on a small dynamical scale. And it has three time scales. And so in practice, what this means is that if you just take a population of galaxies that say, follow some kind of overall halo inflow or accretion rate, and then you can add variability to this by different amounts. So this is just showing you how adding, an overall scatter changes the star formation history behavior. But you can also change the correlation timescales. So this is changing one of the correlation timescales and showing how the variability can either be, short and bursty, like you would expect at for dwarf galaxies or at high redshifts, versus where the equilibrium timescale is much longer and star formation rates tend to be much more correlated the way you'd expect for systems like the Milky Way. So you can do this and you can take all of these, populations of star formation histories along with whatever parameters they're associated and forward model this into distributions of observable space. So things like H alpha or H delta equivalent widths or the 4000 angstrom break strengths and so on. And you can use that to then constrain the parameters of your regulator model. So this is sort of showing if you have a single observation, you don't really get any constraints because as you're seeing from the x's, uh, these seeing a galaxy there could mean that it is consistent to different extents with any of the sigma regulator or the inflow timescales or the equilibrium timescales and so on. But then when you start having populations of galaxies, you can actually use the information in this overall distribution and the covariances between the distributions to actually break these degeneracies and say that I can constrain, the overall amount and time scale of the stochasticity. So this is really cool because simulations show that this is a very sensitive parameter space to the input physics that we haven't really uh, been able to constrain observationally so far. So speaking of simulations, I want to briefly talk about, how you can take all of these quantities that you're measuring from your observations and then start thinking about how you would connect them to feedback and cosmology and these sort of larger scale quantities that we tend to write proposals about. So this was a very first order analysis where we just consider galaxy as made of these three zones: the overall CGM, the circumgalactic medium, the interstellar medium, the ISM of the galaxy itself, and then the central region where the black hole is growing. And so we essentially were looking at how does changing the cosmology or changing the strength of stellar or AGN feedback affect star formation in these galaxies. And because we were doing this with simulations, we could also see how changing the cosmology affects, early structure formation and therefore the potential wells in which these galaxies grow. And we were taking all of this and relating it to the shape of the star formation history on long time scales. So all of this was made possible because people now are talking about running large suites of simulations. So there are things like camels and flamingos and dreams and so on. Camels is this really fun one to play with where there are at the time I made the slide, three suites of 1,000 simulations each, coming from the running the Illustris TNG, Simba, and Astral Galaxy formation models while varying cosmology, supernova, and AGN feedback strengths. Now I think there are more. There's Swift Eagle and a couple more that people have run. And the cool thing about this is they have run entire boxes that vary either the cosmology or the strength of supernova feedback and so on. So you can go in and see as each of these parameters changes, how does the shape of the average star formation history for a sample of galaxies change? And so this allows you to essentially see, as I make, say, ASN1, which is a measure of the strength of supernova feedback higher, how does that actually affect star formation across cosmic time? The issue is that although they tried to match the physical parameters as much as possible, the different galaxy formation models tend to be quite different from each other. And so the uh, precise value of or the meaning of these parameters can sometimes be different. So this requires a bit of careful standardization to compare the simulations on an apples to apples basis. But the real question we were interested in is, can we find a general description of the star formation histories that takes into account the strength of feedback and so on? So we didn't want to be able to understand star formation histories as a function of feedback in the TNG model. We wanted to understand a more general philosophy. So we had this whole process that we went through where we first trained a normalizing flow to essentially learn the mapping between star formation histories over the CAMELS parameter space for all the different parameters across the three models, and went through a phase of equation discovery where we were using these GAMs, which are generalized additive models combined with symbolic regression, and then finally went through a generalization step. So we found a set of equations that relates feedback and star formation history shapes in each of the models, and then we went through a process to fully generalize that. So if you think of a star formation history, this average star formation history in terms of a rising slope, a falling slope, a time of peak, and an overall normalization, then we eventually found a set of equations that describes this as a function of galaxy state variables, things like the halo mass or the baryon fraction or the black hole mass, with some contributions coming from cosmology and some contributions coming from feedback. So the really cool part of this is that uh, even though the precise coefficients might change, the overall form of the equations is the same across all the different simulations, which is really cool because now you get the sort of generalized sense of what's driving the shape of the history. And This one's just actually showing all the coefficients. And the reason this seems to work is because when we do this sort of feature importance study, again, looking at, what drives the star formation rate at a particular time, you do see that at early times it tends to be cosmology, followed by halo accretion at intermediate times, followed by a whole bunch of feedback processes at late times. And this is true across all the different models. So the nice thing about this is that this actually leads us to be able to construct formalisms that allow us to constrain these feedback parameters to some extent, at least, using Galaxy star formation histories as a probe. And so this is something that we can think of in terms of future observatories that are able to, largely sample the average star formation history, be mass complete, and do this across a whole range of redshifts and galaxy types. So that's sort of the overview that I wanted to give in terms of if you care about, star formation history science, here's all the different things that you can think about, and both ways to probe them on individual levels, population levels, and how you tie that to the underlying physics. In terms of, Swara's SIG talking about the different subgroup goals, I think the stuff that I talked about sort of links to all of these at different levels and often provides complementary probes to direct observations of things like, CGM probes or galactic winds or chemical enrichment and so on. So I think that there's a lot of good cross science to be done here as well. And it's also really fun to think about, what can HWO do that goes beyond what we'll be able to do with JWST and Roman. So I've put in 4 questions here that we can answer to some extent with current observations, but then really you need either like deep UV observations or extremely high spatial resolution combined with UV to IR wavelength coverage that would unlock, the transformative potential of some of these questions. So I've put in like the HWO style of like what would be incremental progress versus major breakthroughs for each of these science cases. And I will leave my conclusion slides and open it up for discussion.
Thank you, Kartheik. I really like that you have really looked into the past talks and summarized them.
It was fun to do.
It was totally not expected, but thank you for doing that. So everyone, I encourage you to really go in the summer, I guess, when we run out of talks, you can revisit those that you missed and see what other people are doing as well. So questions from the room. Go ahead, Annalisa.
Yeah, hi, very nice talk. So, I just wanted to ask you, and I'm sorry if I missed this, but like, is your code for the non-parametric star formation histories based on some like synthesis models, like population synthesis models, or not?
Yes, it is. So right now it's based on FSPS. So that means that you can turn all the knobs that FSPS allows for you to, play around with and have that propagated in your fitting. But uh, I'm in the process of moving to this new set of stellar population synthesis models called synthesizer, which allows you to not only combine stellar like SPS models, but also things like AGN and on-the-fly radiative transfer emulators and so on. So short answer, FSPS for now, synthesizer maybe in the future.
Okay, thank you.
Yeah.
Thanks for that question. Any other questions? Go ahead, Casey.
Yeah, no, I love this work, Kartheik. I mean, I'm always impressed by it. Great talk. So I'm sorry, I'm at a coffee shop, so my internet's kind of touch and go. So my question is, like, in terms of the star formation history, my experience is that the histories depend on certain features in the data, right? Like,
Right.
strength of Balmer emission lines or other nebula emission features, UV brightness, work of active rate. Do you have a sense
Yes.
how that's playing out into the remapping that you're going to do to get the star formation histories out? Like, I'm just curious, like, how does it tie back to the certain features in the data? And of course, I'm coming at this from strict observational,
Right.
thinking. So yeah.
Yeah, I mean, so we've been doing this recently in terms of all of these medium band surveys that are coming out of JWST, because you tend to get coverage of different parts of these spectral features when depending on which bands you're looking at. So in a photometric sense, I think as long as you have decent coverage of like the rest optical to 1.5-ish micron portion of the SED, you get reasonable constraints on the long time scale shape of the star formation history. But if you really care about, specific timescales or specific features, like the edge delta absorption, for example, tells you about contribution from the A stars, and that's really sensitive to things like the 600 millennia to 1 gigayear period. I think there it's much better to sort of like take a population, try to empirically calibrate your priors, and then do your fits, if that makes any sense.
Yeah, I agree with you. In fact, I was going to ask if you've been looking at some of that medium band data for exactly that reason, right? Because it should be more sensitive to the features you just described. Yeah. So no, I'm just really curious how it's sort of my training, with Mark Dickinson was always, well, detect something in the analysis, you better be able to see it in the data. And so I think that's kind of the basis for my question. Yeah.
Right. No, and in this regard, I really like one of Vince's clear papers where he looks at these like recently quenched versus old quenched galaxies in the GRISM, and then goes and sees like what's the difference in the SADs. So I feel like we don't have a paper that does that for all the features so far, and I think that's a really cool paper that someone should read.
I agree. Okay. Yeah. I encourage you to do that. Anyway, I love it.
Yep.
Great. Any other questions for Kartheik?
And always like feel free to reach me over email, or if you have any other things you want to talk about.
I'm sure people do. All right. So if there is not any other questions, let's thank Kartheik again, and everyone can have 15 minutes of their life back.
Amazing. All right.
Thank you so much for doing this, Kartheik.
Take care. Pleasure. All right. Have a great day, everyone.